Okay, we will begin on the new chapter, which is the final chapter for the BJT. Finally, we are towards to an end. Okay, on the part 4, which is frequency response. Okay, this one, we're going to analyze the circuit at low and high frequency. Okay, for your information, what have been done, the AC equivalent circuit for past just now, what we have done in the past lecture, that is for the mid frequency. Okay, where you find the voltage gain, the current gain, and everything, that is for the mid frequency. Now we wanted to analyze the circuit, the AC equivalent circuit, by considering the frequency response at low and high frequency. Okay, so good news is, for this one, only covered on the common emitter. Okay, common emitter only. Okay, no common base and common collector. Okay, for the mid band gap just now, for the mid frequency, all cover collector, common emitter, common base, and common collector. So for the frequency response, low and high frequency, only common emitter. Okay. All right. So generally, the frequency consideration, the frequency response of an amplifier circuit, okay, is refers to refers to the frequency range in which the amplifier will operate in negligible effect from the capacitor. Okay, we have all the capacitor. So this range frequencies is mid-range. Okay, we have done that. Okay, that is during the mid-range. Okay, actually, for the case of when you have your cut-off frequency, so frequency response means that this is, wait, okay, mid-range. So the frequency response is looks like this. Okay, so this is the frequency response looks like for the amplifier. Okay, and this is your frequency. Okay, and this is your your AV. Okay, your AV. Okay, the one that in this region, it is actually the mid gap. Okay, mid gap. So this is at mid gap. Mid gap. So this is at low frequency. This is at high frequency. Okay. So this is AV. Okay, AV. So the one that you have calculated in the past lecture, so that voltage gain and everything, it is actually referring to the mid gap. Okay, in mid gap range, okay, we neglect all the capacitor. Okay, where we short circuit all the capacitor. Okay, we short circuit all the capacitor in this mid range or the mid gap. Okay, we short circuit all capacitor. Right, we short circuit all the capacitor. Therefore, that is done for the mid gap. Okay, and then now we want to look at this range, low frequency and high frequency. Okay, what happens to that range? Okay, we will look through it after this. Okay, usually the mid gap over here, it is equal to the, okay, how do you find, okay, so this is at 0 usually. So this is, so the drawing here is, if we want to draw the mid gap, so how do we find the AV mid gap? It is actually, so this is in dB, so AV in dB. Okay, okay, dB. Okay, so this is the maximum point. Okay, how to find the mid gap? Okay, I mean the cut-off frequency. There is a cut-off point. How do we find the cut-off point? It is actually if this is 0, it is must be down by minus 3 dB. Okay, so for example, in this case. Okay, so this is the cut-off frequency. Okay, so where you get your cut-off at low frequency and cut-off at high frequency. Okay, so whatever the value over here, you must drop with 3 dB, okay, in order to get this low cut-off frequency and cut-off frequency. So the purple color here is the cut-off frequency, okay, at low and high. Okay, so at frequency above mid-range, you can still hear me, right? Oh, you have question. Okay, so at frequency above and low and below mid-range, okay, capacitance and inductance will affect the gain of the amplifier, okay, and low frequency, the coupling and bypass capacitor lower the gain, okay. So high frequency stray capacitor associated. So what are these meaning is, okay, so this is how it looks like your circuit, okay. In the circuit, you have all the capacitor. If you still remember, this is what common is this?
Ammeter.
Yes, common ammeter. Okay, so we have capacitor at base, at collector, and at ammeter. So at low frequency, we're not going to short circuit this all capacitor. We will include all this capacitor in your AC equivalent circuit. Okay, remember low frequency includes all the all the capacitor, not the junction. This is the what they call it as the coupling capacitor. So we will include all this coupling capacitor inside the AC equivalent circuit. Whilst in high frequency, you will have to consider the internal capacitor that you cannot see. Okay. For example, here the stray capacitance. Stray capacitance, in other words, is the internal capacitance. So internal capacitance is the capacitance at the each junction, okay, from junction to junction. For example, in here you have your base, okay, collector and ammeter. So from the base to ammeter junction, you have internal capacitance CBE. From base to collector, you have internal capacitance CBC. From collector to ammeter, you have internal capacitance CBE. Okay, and then at the output, the wiring capacitance, because your circuit, so this is the drawing, when you do in circuit on the breadboard and everything. Sorry all, I need to disconnect my headphone for a while, okay, because it is ran out battery. So can you wait? Now can you hear me, everyone? All right, great. Okay.
Yes, doctor, we can hear you.
All right. Okay, sorry, I'm changing. All right, so this is the internal capacitance. Okay, so internal capacitance consists of this junction capacitance as well as the wiring capacitance at the input, okay, which is known as a CW in, and wiring capacitance at the output, which is CW out. Okay, remember, this is still the AC equivalent circuit. Okay, AC equivalent circuit, but okay, the same circuit you draw the AC equivalent circuit, but you need to include capacitor. Okay, for the low frequency, different circuit. For the high frequency, different circuit. Okay, so have you ever heard Bot plot before? Bot plot. Okay.
board plot, okay,
No.
it is so it is plotting. So when you have a graph paper, things like that. So let me show you. So this is interesting. Right. So this is the example of board plot graph. So you have the log scale over here, okay, at this x-axis. So you have 10 to the power of 0, 10 to the power of 1. So because this is online, so difficult for me to teach you the board plot, because in physical class usually I will bring the paper for all the students and you will try to draw the circuit, not the circuit, the graph on your own on the board plot paper. But now it is impossible. But then that's okay. I will show you what is this. So board plot indicates the frequency response of an amplifier. So this is what I told you just now. So the mid frequency, this one we have done this in the past lecture. So in order to get the cutoff frequency, whatever the AV you got here must be minus with 3 dB. And then this line is equal to the cutoff point, where you get your cutoff point at low frequency and high frequency. Okay, so this region is there for the high frequency, this region for the low frequency. All right, so cutoff frequency, the same thing just now. Okay, so this is the graph paper or the semi-log graph paper. Okay, we will draw usually on the paper. Okay, seems like it is difficult and we cannot give you the graph paper during the exam and so on, and hard for you to draw. So then you're not going to draw it. Okay, not going to draw it. Okay, so board plot frequency. This one, how to plot it is, let me show you an example. Okay, so this is just an example. So you can actually solve dB per decade and dB per octave. So in my class, I will use the dB per decade. Okay. Okay, so for example, given the AV, this is, you just have to listen. Okay, so AV 100. Okay, and they want you to draw this low frequency. This FL means low frequency. The first value is so this is the first value, 103 hertz, and this is the third value, and this is the third value, second and third. So you will be drawing starting from the high to the low. Okay, from high to the low. Okay, so from FLE to FLS to FLC. Okay, so this is your board plot. Okay, so you need a ruler and everything over here, but I try to explain my best lah. So just for you to understand. Okay, so although that given AV is 100, but usually the board plot drawing, it is AV over AV mid. Okay, so it is actually equal, it start with 0 over here. Okay, it start with 0. Okay, therefore this is 0, this is minus 10, minus 20, and so on. Okay, so in here, we start with, so every point here, okay, every point here, it will drop with minus 20 dB. Okay, and again, it will drop with another one minus 20 dB again. Sorry, no, minus 40 dB in this case. Okay, so this is theoretically like that. Okay, so for example, the first point, okay, the first point here is 23579. Okay, 23579. Okay, in this plot, I drawn it 10. Okay, this is 10 hertz. Since this is semi-log, so 10 This is 20, 30, 40, 50, 60, 100. Okay, after 100, because this is semi-log, this is straight away 200, 300, and 1000, and so on. Okay, so your first value is 23579. Okay, so this is your point of 23579. Okay, so this is your starting point here, 23579. Okay, so this 23579, okay, will be dropped by 1 decade by 20 dB. Okay, so 23579, if you divide by 10, you will get about 23.5. So where is 23.5? So this is 10, 20, 30. So where is 23.5? It is here. Okay, about here. Okay, I don't know why it is written here. So it is about here. So you have to draw a straight line here and then drop by 20 dB. Okay, draw a 20 dB here. Okay, straight line like this. Okay, and your 23.5 is equal to around this region. So the intersection here, you draw a line over here. So you will get 1 point by first point, 235.79 over the 20 dB. So you will get like this, and then you will do so on, okay, for another frequency here. Okay, all right. So this is not coming out for your exam because you don't have to draw lah. But then the explanation is like this. So you have to actually, so I maybe next time I need to have a plain paper and draw it. Okay, so we go back to here. Okay, I need to confirm again. Okay, so it is hard for me to explain because I need a roller and a pencil to explain this. But what I can say to you, so every time it is divide by 1 decade. So therefore this is maybe your 23.5. Okay, so this line of 23.5, okay, will go the intersection here. So you have this line over here, but where does it? So this is the intersection line. Okay, this is the intersection line over here. Oh, sorry. Okay, but then it stopped here. Why it stopped here? Because the second frequency is 103. Okay, that's why it stopped here at 103. Okay, 103 something. Okay, therefore there you go again, 103, 10.3 is over here. Then you do the same thing here. Okay, but now it dropped with 40 dB. Okay, just now dropped to 20 dB. You get a straight line over here until here. Now you drop with 40 dB. Okay, and so on. Okay, so the line, the only line that we wanted you to draw, this line. Okay, this line. All right. Okay, so for the common emitter, let's go straight for the low frequency response. Okay, so this is the circuit. Okay, you have the, for low frequency, you have to include all the capacitor that you see from the circuit. So in this case, this capacitor must include, this capacitor must include, this capacitor must also include. Okay, so for the low frequency, I believe that all of you know to draw the AC analysis, base, collector, and emitter. So this is common emitter. Okay, see, this is the AC equivalent circuit. Okay, this is base, collector, and emitter. Okay, from base to emitter, you have R pi. From collector to emitter, you have GMV pi. This is the same AC equivalent circuit. But then, as you can see here, all the capacitor are being placed in the AC equivalent circuit. Okay, the drawing is still the same. Okay, from base, you have from base, you have this R1 and R2 in parallel. Okay, but still, your voltage here is grounded. Okay, but capacitor not short circuit, but you include the capacitor. Okay, at base, you have these two resistors, okay, in parallel, these two resistors in parallel to the ground. Okay, And also at base, you have CS, then you have to put your CS over here. And then you have resistor RS and VS, then you have to put also in your circuit like this. Okay, now let's take a look at the ammeter. So ammeter, you have RE and also capacitor CE. Put everything here, RE and capacitor CE. Okay, and at collector, you have RC to the ground. Okay, RC to the ground. Okay, and then also you have this capacitor CC to RL to the ground. Okay, CC to RL to the ground. Okay, so in here, this is your V out. Okay, this is your V out. All right. Okay, so how to find the capacitor? Okay, how how to find the frequency? Your objective is to find frequency. Which frequency? In this case, you're gonna have three frequencies. Okay, three frequency. Which frequency? By referring to this frequency, we call it as a FL, referring to the source. Okay, FLS. And also you will need to find the FL referring to the emitter, FLE, and you need to find also this frequency referring to the capacitor. So this one, the objective is to find all these three frequency, okay, all these three frequency, all right? So let's take a look on this one. Okay, so for first one, okay, in order to find, okay, let's start first with this one, FLS first. Okay, so when you want to analyze this FLS, okay, this frequency referring to the CS, what happened to this other capacitor? All this will be short circuit. Okay, and then you have to redraw again the AC equivalent circuit by short circuit this all capacitor. Okay, in this case, okay, if you want to find the CS, okay, FLS, okay, FL referring to the source, okay, what happened to the other capacitor where CE and CC will be short circuit. Okay, only left with this capacitor. All right. So in this case, okay, we know that if you still remember, so F, okay, okay, F is equal to the 1 over 2 pi RC. Okay, so in this case, we will have to find, as you can see, in this case, F is equal to the 1 over 2 pi RC. Okay, what will be the C over here? Since this is referring to the CS, so this is CS. So what will be the R? So R that you are seeing from here. So this R, we call it as the R that you can see from the total over here. Okay, so let's take a look here. So if I redraw again the circuit, okay, okay, so this CE is short circuit. Okay, so this CE is short circuit. Therefore, what happened to RE? Guys? Yes, short circuit. That's why there is no RE over here. Okay, so because of the CE short circuit, therefore RE also short circuit. Okay, that's why no RE over there. Okay. Okay, and then, all right, so what can you see from here if I draw the equivalent circuit? So, all right, so what are the total resistor you see from this node? Okay, from this node, what are the total resistor? So if I draw again the circuit, I need to make it smaller a bit so that I have space to okay. All right. Okay. So in here, we draw again the circuit. So all the resistor that you can see from here. Okay, so if we draw again the circuit, so the voltage source is short. Okay, so resistor here RS. Okay, and then you are seeing from here. Okay, what are the R total over here? And then you have RBB, which is R1 parallel with R2, and then you have your R pi. Okay, R pi. So can someone give me what is the R total here?
R1 parallel R2 parallel R pi plus
Yes.
RS.
Yes, correct. Okay, so they don't use this as okay, whatever. So they put this Z in. So Z in, it is actually equal to the R1 parallel with R2 parallel with R pi. Therefore, R total is RL plus Z in, which is equal to the RS plus R1 parallel with R2 parallel with R pi. Okay, like this. Okay, so in here it is equal to the R total. So this frequency is FLS. Okay, FLS. Okay, so you have all the resistor value as well as the capacitor value also given, and 2 pi, of course, you know. So you will get the frequency for this one is equal to the 1 over 2 pi RT times CS. Okay, before I move forward, do you have any question on this? Again? Any question? Hello? Hello? Can you listen to me?
No question, madam.
All right, no question. Okay, great. Okay, so this is one, okay, for number one frequency. Okay, okay, number one. Okay, oh my God. Okay, number one. Okay, so we've done this. Okay, number one. Okay, now let's derive for this one. Okay, number two, this frequency. Okay, so what happened if you want to find the frequency referring to the CC? So all this capacitor also shorted. Okay, this CS short, CE also shorted. Therefore, you need to redraw again the circuit. In this case, okay, CS and CE short circuit. Okay, therefore RE also short circuit. Okay, so you redraw again the circuit, okay, and just remain the C2 over here. Okay, now you know that the FL is equal to the 1 over 2 pi RC. Therefore, this C is referring to the CC. Okay, this is CC, and this R is the R total that you see from this node. Okay, I need to make it smaller, this one, so that I can draw for all of you. Okay. All right, so this is how it looks like. So if we draw the circuit, so it will be like this. So you have RC, and then you have here, sorry. Okay, you have here your RL. Okay, whatever resistor you see from this node. Okay, since they put Z out, I want to put Z out too. So Z out is equal to what?
RC.
Yes, RC. Okay, so what will be the R total over there? It is not parallel, student. You see from this node to down, okay? So all these resistor actually in Series.
Series.
Yes, do not get confused with it. Okay, most of the student in the exam do parallel. No, it's series. Okay, RC plus RL. Okay, RC plus RL. Okay, or in this case, it is equal to Z out plus RL lah. Okay, so that's the same thing over there. Okay, so Z out plus RL. So this is your RT. Okay, so this is RT, Z out plus RL, and CC given. Okay, that's it. So this is the coupling capacitor number 2. Okay, let's take a look on the number 3, this one. Okay, this one. So this one, okay, what happened to the CS and CC? Both will be shorted. Okay, in this one, both will be shorted. Number 3, it is, in this case, CS and CC short circuit. Okay, you redraw the circuit, you will get like this. So only CE left here. Okay, only CE left here. Okay, do you have any idea how to get the R equivalent? Do you still remember the unbypassed common emitter? How do you get the R equivalent over here? By using what? Still remember? Common
Z-test
emitter. Yes, common emitter unbypassed. Okay, so by using, okay, to find this is by using Z-test over I-test. Okay, Z-test over I-test, which is the same thing lah, which is you have, okay, I think I want to derive. I have time now so that you'll be much clearer. Okay, to find R equivalent, okay, by using V-test and I-test. Okay, so we draw again the circuit. Okay, inject imaginary voltage V-test. Okay, here, okay, you detach first the RE, so you will get inject V-test over here. Okay, you will have the V-test I-test. So I have time, I rajin sikit, I want to do it for you. Okay, so you have here this one minus plus V-test. Okay, and then you have over here okay, GM V pi, and then you have here R pi. Okay, and plus minus V pi. Okay, all the resistor here. So what are all the resistor? Because when you inject, okay, you inject V-test by using V-test and I-test injection. Okay, V source will be short circuit. Okay, when this V source short circuit, therefore what are the total resistor here at the input here? Can I say, is it because this is short circuit, so you have R1 and RB in parallel? What happened to RS? Also?
Parallel also.
Yes, parallel also. Okay, so this one will be RS parallel with R1, parallel with R2. Okay, all right. So in this case, this is your I-test. Okay, how do you get it? Okay, if you forget whatever, okay, you can always watch it, the video. So you apply KVL over here. Okay, so in order to get this, so Z-test is over here. Okay, how do you get Z-test? It is actually equal to the V-test. Oh, why keep. Okay, so it is actually equal to the V-test over I-test. Okay, so in this case, okay, V-test is equal to the total voltage at this KVL. Okay, therefore it is equal to the IB plus R pi plus R1 parallel with R2 parallel with RS. Okay, so you need to find here lah the KVL. So KVL here, it is actually, this is IB, okay, IB, Okay, so apply KVL. I hope you know. So current at RS here also IB, same like R pi. Therefore, total voltage across this loop is equal to the IB, R pi plus R1 parallel with R2 parallel with RS. So I test, what will be the I test? So I test is the total here. So it is actually equal to, this one equal to the beta IB, because it is at node capacity collector. Therefore, this one I test is the total current here at this node. What are the current in here? Which is IB and beta IB. Okay, so I test here is IB plus beta IB. Okay, cancel out everything. So you will get here R pi parallel A plus R1 parallel with R2 parallel with RS over beta plus 1. Okay, not finished yet. This is just for the Z test. So R equivalent, okay, that you can see from here, it is actually equals to, so you have this CE where you see from here. So R equivalent, it is actually equal to the, you have RE and Z test. Okay, in this case, it is parallel or series?
Parallel.
Yes, so RE parallel with Z test. Okay, that's how they solve it. So for FLCE, FLE is equal to the 1 over 2 pi R equivalent CE. So R equivalent this is equal to this one. Okay, so this is your Z test. Okay, that's how you derive it. Okay, all right, so we've been keep repeating over and over and over again the derivation because of exact test is quite related for the common collector, similar to the common emitter. Please do again the example. Okay, so I hope that you will be faster in understanding to derive it because you haven't done anything yet on the example. I mean, like some of you has done. Okay, I will upload some tutorial question. There will be a good practice for you, but then try to derive it again and again so that you will be much clearer. Okay, so this is just for the case of low frequency response. Okay, so the analysis is quite similar for the mid frequency response that we have done, but we have to include all the capacitor. Then we find one by one the frequency referring to that particular capacitor. So in this circuit, it has 3 coupling capacitors, CS, CC, and CE. Therefore, you're going to have 3 circuits, okay? We're referring to the CS, CE, and CC. So we have done this, okay? Okay, do you have any question? So can you all try this example one before the next class? Okay, so that next class, I will just go through on the answer. Okay, can I trust you to try this example one?
Yes.
All right. Okay, thank you. Okay, so I think I want to stop now because already 12:55. If you have any question, okay, so your friend said just now, so Bezen have question page 70. This
Yes.
page 70 or the previous page
previous one.
70? The previous one, okay.
Ah,
All right.
with the drawing one.
Wait, I need to open again. My right. Right. Okay. Okay, so please try the example just one, okay? Just now, okay, for the low frequency. All right, so Bezen, you have page 70. Let me go page 70 straight away. Page 70, this one. All right. This one, Bezen? This one?
Yeah.
All right, okay.
Yes, this one.
All right. So what is the question?
At the emitter junction there.
Yeah, emitter junction over here. Okay, emitter
Is
junction. This one?
is it like this one is because according to the conservative of charge, the law of conservative of charge, the current going in E must be going through the two branches, right? Why is it equal to negative IB?
Again, one more time.
The current IE going into junction E should be distributed to the both junctions, right?
Yeah.
Why? And then why is it only IB, only negative IB on your sec
No,
E?
not negative IB. So here I put it is equal to negative IB beta plus 1. It is IE. IE. Here. Why it is negative IB? Because IB is in the negative direction. Still, this is actually IE. Okay, this is IE, not IB. IB beta plus 1, which is represented as IE. I didn't take it as IB, I took it IE over here. But I changed to IB beta plus 1.
Oh.
Okay.
Okay.
All right, are you clear? But why negative? Because I changed to IB beta plus 1, but IB in this case in opposite direction, it is negative. So I put negative over here. Okay?
Okay.
All right. Okay.
All right. Thank you.
Okay. Welcome. Okay, so if no question, I think frequency response is I can see easy. Easy if you already clearly understand on the derivation of the AV, on the input impedance and output impedance at the AC equivalent circuits. Please do practice on that. Okay, although I have derived it for you and discussed the example, derive it for you, it will be no wrong if you do it on your own again, okay, for your better understanding. All right, all. I think that's all for today. Okay, see you on the next class.